In the spring, I didn't make any instructional videos because I'm lazy and because I just felt like someone else out there could do it better. I figured we don't need all the teachers across the country to suddenly learn how to make great instructional videos. If our curriculum is going to be standardized, what we really need is just one teacher to make them all for us. This year I've given in. I'm not going to be that one teacher with my boring monotone voice and my chicken scratch writing, but I've actually found the process is kind of fun, but time consuming, but fun too. Like for my Course 2 class, I made one where I wrote and talked at the same time, but then the audio came out bad and you could hear every click of the keyboard. So I went back and reproduced the audio, except this time I acted like I was a commentator, like a sports commentator who wasn't sure what was going to happen next. CPM does have a lot of concepts that you ideally think about first, get confused about, and then we go over as a whole group. I'm not sure that we'll have time for that last part as much this year, and when we do, I fear we'll rarely get that cognitive sequence just right. There are some substantial drawbacks to teaching this way, namely that I don't get any feedback from my audience. And there are also draw forwards. That's what I'm calling pros. Not pros like writing style, more pros like the opposite of cons. Like I can go on rants and tangents whenever I want, and I can force you to listen to my inner monologues. This is kind of like therapy for me. Also, I can speed up and slow down the video and even make it go in reverse, control the zoom, add animation effects, and I can even make something explode at the same time that I say boom. And I figure if I get tired of trying to fit a square test into a round peg hole, I could try some kind of project where you teach a concept on a video, and you get graded on content, but also rewarded for creativity. Then I'd already have the models to show you what I mean. I could be the floor, and Vihart could be the ceiling. So you've probably seen these numbers before. These are all perfect squares. I don't have to list them, you've seen them before, but there is a little bit of a pattern to them that I'm sure many of you have picked up on before. To get from 1 to 4, I go up by 3. To get from 4 to 9, I go up by 5. And there's a pattern that continues in that fashion where it goes plus 5, plus 7, plus 9, plus 11, plus 13, plus 15. And then if I want to use that pattern to see if it's right, I may not prove it's right, but I may get a strong inference that it's right by using it to predict the next number to see if that's correct. I could go plus 17 and I get 81. And I know that that's the next square number, so it seems like a pretty good pattern that I may be able to use. And I can actually look at the perfect cubes in the same kind of way. The perfect cubes written out are 1, 8, 27, 64, 125, 216. And if I look at what's happening here, at first I go up by 7, and then I go up by 19, and then I go up by 37, and then I'm going to go up by 61, and then I go up by 91. So it doesn't seem to be the same exact pattern, but let me just look a little further in here and see what's going on in like the scene behind the scenes. So this is from plus 7 to plus 19. I'm going up by 12. Then I go up by 18. And then I go up by 24. And then I'm going up by 30. And then I assume the next number I would go up by would be 36. So now, okay, so I could actually test if this rule works by figuring out what the next one will be. If I'm going up by 36, then let's see. How would I figure this out? Okay, I don't want to do the math in my head, so let's see if I can figure out. If I go up 36 from 91, I'd be at 127. So where would that leave me at? That would leave me plus 127, but I have to go plus 127 from 216. So if I go up 127 from 216, I'm at 343. Now is that the next perfect cube? Is that the same thing as 7 cubed? It is. So my rule worked. Okay, this is going to be the first of many times in this course where we're talking about a second degree difference. We're not just talking about the rate of change, like the slope. We're talking about the slope of the slope, or the rate of change of the rate of change. And I used to teach this concept using a ruler and a chalkboard, and I'd show how the ruler, which can be shown to be tangent to a curve at any point, if you move it from left to right on a curve, the ruler is either going to rotate clockwise or counterclockwise. So I'm going to do my best to mimic that process with the Desmos, and I'm creating a function here, and I'm creating a point, and I'm going to try to create a line that's tangent to the function at that point. And then when I do that, I'm going to move that point from the left to the right. And actually, what I want first to happen is I want that line to be dotted, and I want it to be black. So let's fix that. Not orange, I want it to be black. And think of what's happening, or watch what's happening. This line is rotating, the point is moving from left to right, and that line, that horizontal line, is going to rotate, in this case, counterclockwise. Up until a point. Now at another point, it starts to rotate clockwise. Okay? Watch again, it's rotating counterclockwise, and then it's rotating clockwise. And when it's rotating counterclockwise, like in the first part from -3 to 0, you can sort of think of that as going from very negative, the slope is negative, it goes to 0, and then at some point it gets to be positive. And so the slope is increasing. It's going from negative to 0 to positive. Okay, one more time, it's going from negative to positive, and then it goes from positive to negative. Okay, so for the last clip, when I was writing, and I put the music on to spare you from my voice, what I was trying to show you is that in a quadratic function, the rate of change is not constant, but the rate of change of the rate of change is constant. So that's the second degree differences. So this is what the CPM topic on finite differences is all about this. So just to be thorough, why don't we inspect a cubic function, and let's see if we get a similar pattern to the past ones. And so what happens, and you might have been able to predict this, in the cubic function is it's not the second degree finite differences that are constant, it's actually the third degree finite differences that are constant. In this case, they're constant at +12. So that's like not the rate of change of the rate of change, but the rate of change of the rate of change of the rate of change. And if you remember, we did a cubic function earlier on where we got constant third degree finite differences, but in that case, they weren't +12 every time, they were just +6. And that was just a function x cubed. And so you might be wondering, why did we get third degree finite differences of +12 this time when the other time we got +6?